Thank you very much. Welcome, everyone. My name is Gábor Tornai. Yeah, let's get this on the road. Okay, I'm going to be speaking about two things today, or we are going to touch two fields. The first field is machine learning, and the other field is quantum chemistry. I hope it will be at least understandable and you will enjoy this small talk. Okay, first, a short motivation. What is quantum chemistry? What's the bottleneck? What's the field we are working on? Quantum chemistry is a field where you use computer simulation for chemistry, actually, where you take into account a lot of things, a lot of quantum related things, but also you leave out a lot of things because it just becomes computationally too expensive. It's used partially for drug discovery in the very early stages of drug discovery, material science, reaction mechanisms, even molecular dynamics, but that's less of a field. It's more like a molecular mechanics kind of things. What we focus on is an algorithm called self-consistent field, which is an iterative process. We will be talking about I hope in the next slide. Typically, all the quantum chemical algorithms I'm aware of, they are iterative. Depending on the initial guess and the task size, you have a wide range of iterations till convergence. Typically, an SCF algorithm requires between 6 and 30 iterations. And the problem scales, the problem size scales to like 2.5 or the fourth order, depending on what kind of smart algorithm you are using. What we were thinking that, okay, a lot of effort has been made to make the iterations itself faster. But what if we would put a bit of effort that choosing a better initial guess? Would that help solve a bit of, save a bit of time? Let's see. That's the main logic behind this project. In a nutshell, what's an SCF problem and what's an SCF algorithm? We have an initial density, electronic density. We build the operator, the Fock operator. We make a few mathematical calculations like diagonalization. We update the electronic density, and we check whether have we converged or not. It seems, I mean, in a nutshell, that's very, very easy and very, very simple. Actually, it's a very robust algorithm itself. With a better P, with a better electronic density, with a better initial guess, we will get fewer iterations, faster science. Typically, as I mentioned, the number of iterations, the time required for an iterations, depending on the system size, is typically from the seconds to the hours, or even sometimes days if the system is extremely large, but still computable. Yes. What kind of initial guesses we have there? We have a core Hamiltonian kind of gas, which is a very, very poor gas. We have a Hückel gas, which is has limited accuracy. We have the superposition of atomic densities called SAD. Currently, nearly everybody uses that or some kind of variation of that. So the main question is whether can machine learning do better, or at least can we reach the break even for this battle-tested gold standard initial guess? Like provided we learned from millions of converged SCF calculations, can the model, not we, the model, can the model at least get a bit of chemical bonds or yeah, so you get the picture. What is the SAD or SAD, the superposition of atomic densities? How does it work? It's actually very simple. Each quantum chemical software has practically a big database, a pre-computed database, where they pre-computed all the atomic density of each element. And during runtime, they just simply put them together into the density matrix. So it's very fast. It's actually a lookup and a bit of addition. It automatically satisfies all the physical constraints needed for an initial guess. It's practically independent of the system size. I mean, scales normally with the system size. And as I mentioned, it's widely used. It's okay. The best we have so far. But obviously, if it's just based on atoms, it ignores the bonds which are already present, I mean, which are present in a system. There are no kind of polarization, no charge transfer. For example, it would be the same gas for benzene, which is a fully aromatic, or cyclohexatriene, which is the same atoms, but a different bond structure. So with a different, so we have these two molecules which have different bond structures, but the SAD would give us the same gas. Okay, so as I mentioned, our goal is to match the SAD performance with a machine learning model. Our approach is a density transformer-based density matrix prediction model. We have 3 layers. The input layer, you only need the coordinates, the atom types, some categorical features like which level of theory we are using, other parameters. Those are not too interesting, and zeroth order estimates of the densities. These are not the SAD-based densities, but those are calculated from our training set, that how the atoms are. For example, we have a carbon atom. What is its average density over 10,000 or 100,000 cases? What is its average density? So that's like a baseline. It's actually that's terrible for an initial guess, but that's our baseline. Then we have block which we call molecular block. Those have 4 parts: an attention for the coordinates, a multiple layer for charge again a multiple layer for first, second, third, and the fourth multiple of the electric charge, and we have some other parts of the model. And those are mainly for evaluating the state and some residual summation and scaling of how to scale each part of the molecular block. And this molecular block is placed 5 times after each other. The state is transferred between each blocks. And we have the output heads. We have an energy output. We have a charge distribution output, this molecule, that's a charge distribution kind of thing. And we have the density head, which is what is our main goal. So actually, practically our input is only the coordinates and the atom types, and the output are the density matrix tiles for the atomic blocks. And our model currently, that's only 3 million parameters. You can say that, okay, that's really much, or you can say that's really tiny. In the world of transformers, or compared to any kind of language models, or not language models, but large machine learning models, that's a small model. Why transformers? Because you can process all atoms simultaneously. There are no bottlenecks. You can batch multiple atoms or multiple systems efficiently. Yeah, it's a GPU-friendly way of doing things. There are a lot of additional benefits. Yeah, it has been done in JAX-Flex. First, it was made in TensorFlow, but after Google retired TensorFlow, we have to change, and we choose JAX-Flex. Yeah, it has its highs and lows. Yeah, so the architecture is very favorable for the GPUs and naturally maps that. We also do a bit of post-processing where we I said inject physics. Actually, we just do a bit of linear algebra, which makes our results conform with the physics. That's all, like hermiticity, idempotency, electron count, and so forth. That's it. That's not important. Okay, the training data set. We have 1.2 million molecules. We have several kinds of data sets. All of them were generated by us. These are not equilibrium state geometries, so these are not optimized, but they are just roughly good geometries. But that's actually a good thing, because in this case, our system will be able to generalize not just the best geometries, but any kind of noisy geometries as well. We have a tree. Oh, okay. What does it mean, tree? That we start from a seed atom, and we add atoms, so forth, till it grows. We have also mutation in there, and so forth. We have a combinatorically exhaustive set of small molecules, starting from 1 atom till 4 atoms. We do not count the hydrogens, only the larger elements. So we have a combinatorically exhaustive set combinatorically exhaustive set means in this case that the 2D molecular structure, the element variation, the valence, and the bonds are all taken into account. Yeah, there are different variants and so forth. So this is our training set. It's quite big. It was, I don't know, at least half a year till all was generated and calculated. It's quite big. It's quite diverse as well, with different species like charged and radical and different spin states. That's 5 minutes. Okay, then okay, that's the test set. You can see here the element distribution. We have, unfortunately, it's not, the test set is completely different from the training set, so that these are standard test sets. The GMTKN 55 filtered for the first 3 period, and the QM9 dataset uniformly sampled. What we have, that's the take-home message actually. We have parity with this set, with the superposition of atomic densities. In 50%, practically 50%, we are equal. I mean, we need the equal number of iterations. In the remaining, in 1/4, we are better, and in 1/4, we are worse than the SAD. The mean difference is 0.21 iterations for the SCD. So we have not reached complete equality, but actually that's a 2% overhead for the SCD. So that's, we can say that that's quite okay. So that's the main result. So we have achieved what we aimed for with this small model. This is the distribution of the time difference. As you can see, the y-axis, that's a logarithmic axis. I must note that you can see that in the majority we have equal iterations. This is a slight advantage for us, and so forth. That's not interesting for now. The quality of the result is practically the same. We have a lot of challenges. The test set coverage and so forth, that's not completely is what is possible in the chemical space. But we will work on it. Here also in the test set we have holes in what kind of pairs are there in the test set. That's a given. Here also you can see that there are cases where we are better or where we are worse than the SAD. This is also the time saved. So again, the gain distribution or the anti-gain distribution in our case, but we can see that we are quite even. There are variations, obviously. That's not interesting. What is the future? That we have a bit of overhead, but this overhead can be solved by streaming a lot of molecules at once. This is an engineering problem, actually, which is solvable. So that's the main take-home message. And the second one is that it's still a tiny model. With a bigger model, with more models built into one cascade, we are sure that we will get even better result. Actually, that's I think that's okay. We can, and yeah, but that's not important. Taking into the time is over. Thank you very much for paying attention. And if there are any kind of questions, I hope I can answer them.
Thank you for the nice talk. So then is there any question again?
Hi, thanks for the nice presentation. I mean, you mentioned that in your training set, you fix the positions of the ions, but I guess in your final goal, the chemical quantum chemistry calculation, I mean, at some point you have to let the ionic force to move around and find their equilibrium position, or how is it handled in your case?
Yes, that's a different kind. That's the next level of the algorithm. First, you calculate the electronic state of that given configuration. And that's an algorithm called geometry optimization, where according to its forces, this geometry is optimized and you find the new geometry or the optimal geometry for that exact parameter set. Depending on the parameter set, that has a slight variance. That's the next level of the quantum chemical algorithms in this level of theory. We are working on the force estimation and also that how to step, but that's still a work in progress. Yeah, so that's also on our plate, but we do not have.
So what you mentioned that your 30 iterations taking minutes to hours and maybe days. This is actually only for one step in this process.
That's right. That's right.
Orders of magnitude more of the.
Yes, and for geometry optimization, you usually have much more steps, like step in the 50s or in the hundreds than have, and that's why there it's even more important to have either a better initial guess or a better stepping strategy. Yeah, that's also on our radar. Thank you for the question.
Thank you. So do you intend to use this software as a preprocessor for known quantum chemistry softwares, or?
Yeah, that's correct.
Okay.
The company I'm working for half-time has a quantum chemistry package, and we are collaborating with QChem. That's also a large known quantum chemistry package. It will be released in a bit of time. I don't know when, but it will be released, and it will be released to the public.
Okay. Can this initial guessing method or no? Okay, so this initial state preparation method include external fields like electric or magnetic fields present?
Currently not.
But there seems to be no obstacle, just another.
Yeah,
okay.
I know.
Okay.
That's a known obstacle, or that's a known quality. But those can be included later. Based on our experience with transfer learning, with much less training data, these kinds of effects can be included, but we do not have conclusive results regarding that direction.
Thank you very much.
Thank you so much.
A very interesting talk. So in many machine learning for molecules, they use graph neural networks and you use transformers. Have you considered graph neural networks for this specific task? Are there any advantages, disadvantages? What do you think?
Actually, I was not responsible for that part, so I can't answer you as of now. But if you write me an email, we can discuss the particulars regarding that.
Thank you for the nice presentation. I was wondering if there is significant effort went into creating machine learned force fields from DFT data. And I was wondering if there is a possibility to use that as well to have like some good guesses for the initial state, or is there something that might be interesting?
Can you pose again the question? I'm not sure I get what you are asking. You've mentioned the machine learning generated DFT functionals. That's one part, but
Yeah.
I'm not. Yeah.
So maybe we can discuss this after. But my idea was that there are some. Maybe let's discuss this after the. Thank you.
Okay.